All right, guys, let's go ahead and get it started in here with these intro to UCM notes. So these notes are going to be pretty math heavy and they're going to take a little bit of time, and I apologize in advance for that. But just make sure that if you're confused at any point that you're pausing the video and rewinding, because this is a very difficult topic. All right, so let's take a look at our first problem here. We have a satellite orbiting the Earth, and here's all of our information. Up here, we see that we have a bunch of equations that we're going to get to in a sec, as well as some useful information. The first thing they want us to do is draw a diagram of that shuttle orbiting the Earth, and then they want us to answer a few questions in regards to that. So I'm going to go ahead and draw my picture of my satellite. So here's my little satellite. All right. And then I'm going to go ahead and draw the Earth. Here is the Earth, round, some might say, right? And then we have that satellite moving around the Earth, and it's going to move in an elliptical path. All right, so I'll do my best to draw that. I'm not the best artist, but here we go. It gives you an idea of that. It wants us to identify what the centripetal force is. Well, a centripetal force is a force that acts towards the center of an object. And what we mean by that is essentially what force is going from this satellite towards the center of its orbit. So what is this force that I drew this vector for? Well, we know that the satellite and the Earth are attracted to each other, and they're attracted due to gravity. So in this case, and in all cases when we deal with uniform circular motion in space, it's going to be force gravity as our centripetal force. All right, next it says to draw that force on the diagram, which I already did. I pointed it inward because the centripetal force points perpendicular to our path and points directly towards the center. Letter B, calculate the shuttle's centripetal acceleration. Does this acceleration seem very big? What does the value of the acceleration tell you about the shuttle's motion? So there's multiple ways to do this. And let's just go ahead and look at our equations and see if we can figure it out from there. So if we look up here, we're going to see that we have multiple equations. This one has acceleration in it, and so does this one. This also has centripetal acceleration. Because I know how to do these problems, I'm going to go ahead and use the correct equation, and that's Newton's second law, saying net force equals ma. So net force is equal to mass times acceleration. How did I know to use this equation? Well, the questions are kind of guiding me in that route. It talked about centripetal force here, so I had an idea that if I'm going to solve for my acceleration, I'm going to need force to do that. So this equation can actually be rewritten as net force centripetal, lowercase c, is equal to mass times acceleration, centripetal. Same thing, I'm just adding a c subscript. So net force centripetal are all the forces that point centripetally, and that's only force gravity. So we can go ahead and plug in force gravity here and say force gravity is equal to mass times acceleration centripetal. But since we're in outer space, we can't just use our old-fashioned force gravity equation. We need to use our new one. And that's going to change this whole equation into the following. Big G times m of the satellite times mass of the Earth divided by r squared. And this is just my universal law of gravity, and we have that up here as well. I know that this Fg is equal to mass times acceleration. The question is, though, what mass is this? And if we look back at our equation over here, we know that it's the mass that's experiencing centripetal acceleration. Which mass is experiencing centripetal acceleration in this problem? Well, that's going to be our satellite. And again, how do I know that it's a satellite? Because the centripetal force is acting on the satellite as well. So go ahead and add that S subscript below. Now we can just go ahead and solve. We're going to notice that we have a mass of the satellite on one side and mass of the satellite on the other. So we can get rid of one of those terms. And we find out that centripetal acceleration is just equal to big G times mass of the Earth divided by r squared. Now that we have our equation, let's talk about what each of these variables are. Well, we know mass of the Earth is just mass of the Earth, and that's a value that they give us up above, and that value is actually 5.98 times 10 to the 24th. And then our next one is big G. We know that because that's a constant. That's 6.67 times 10 to the negative 11th. And lastly, we have R. And R is the distance from the center of one of those objects to the center of the other object. And in this case, the center of the Earth is right here, and the center of our satellite is right here. So we're going to need to take the distance from here to here and add it to the distance from here to here. So this R is actually going to equal the radius of the Earth plus the height of the shuttle above the Earth's surface. All right, now that we have all these numbers, we can just go ahead and plug them in and solve. We find out that the centripetal acceleration is equal to 8.8 meters per second squared. Make sure that when you guys are solving this, you're putting things in parentheses just like before, right? The top in parentheses and the bottom in parentheses. This R value needs to be squared. So please remember that after you add these together to square that final result in your equation. It asks us if this acceleration seems very big. This is just a general question to get us to think about numbers and think about past and future problems. I'm going to say no, and the reason why I'm going to say no is because it's smaller than the acceleration due to gravity usually is, which is about 9.8. This is only 8.8, so it doesn't seem that big to me. What does this tell us? Well, this is interesting. What this centripetal acceleration is telling us is the same thing that regular acceleration is telling us, and that's how fast velocity is changing. In this case, though, the velocity of our spaceship is always changing because it's moving in a circular path or an elliptical path. Velocity at one point might look like this, right? It might be pointed this way. And then a few seconds later, at another point, might be pointed this way. What's interesting, though, and we'll talk a little bit more about this later, is that the velocity here and the velocity here have the same magnitude. The only thing changing is the direction that the object is moving in. So what does the centripetal acceleration tell us? It tells us how quickly the direction is changing. All right, our next question is number 3, and that says calculate the shuttle's velocity. Which direction does this velocity point? Is it pretty big? All that good stuff. Well, I already spoiled that for you, and the velocity is actually going to point tangent to our orbit, or in other words, perpendicular to the centripetal force. Now that we know which way this velocity points, we're going to go ahead and solve for it. So our equation is going to be AC, centripetal acceleration, is equal to v squared over r. And this is just in our table above right here, okay? So nothing new, it's just an equation I'll give you every time, and it just tells us how those two variables are related. So once we have this, I'm going to go ahead and solve with the variables and manipulate velocity and then plug my numbers in. Multiply r to the other side and then square root it. I find out that velocity is just equal to the square root of acceleration, centripetal acceleration, times r. And again, I just rearranged some variables to get this. I multiplied r over and then square rooted the whole thing. Next, I'm going to go ahead and plug my numbers in and find out that the velocity is 7,696.86 meters per second. So now we need to think, is this a big number? Yeah, this number is huge, right? Relative to what we've been talking about with kinematics and stuff, this is a ginormous number. And again, there's no right or wrong answer when I ask if this number is big or small. It's just to get you thinking about previous questions and future questions. but I would say yes, this number is big. Something important to note about velocity, like I said before, is that velocity is always changing when it comes to centripetal motion. The magnitude, though, of the velocity is not changing. And if you remember, this is kind of a little bonus question for you. The magnitude of velocity is just speed, right? Because speed does not have direction. Therefore, we can say that uniform circular motion, speed is constant. Now let's take a look at letter D. And letter D wants us to calculate the period of the shuttle around the Earth and convert this period into meaningful units such as minutes, hours, and days. So let's go ahead and do that. Well, first thing we need to think about though is this new word period. We haven't talked about it before, but basically a period is just the time it takes to complete one cycle. So if I were to ask you, well, what is the period of the Earth around the sun? Well, the answer to that would be 1 year, right? It takes 1 year for the Earth to complete one cycle around the sun. So if I asked you, what is the period for the moon and the Earth? Well, that would be around 27 days because it takes about 27 days for the moon to orbit the Earth. Well, let's go ahead and solve for our shuttle problem here. And in order to solve for this period, we're going to need to take this equation. Distance equals rate times time, because the time is the period in this equation. So I'm going to go ahead and bring that down below. So D equals V times T. Awesome. I just solved for V in my last problem, right? I said that V was equal to 7,696.86 meters per second. What is T and what is D? Well, like I said, T is period, so that's what I'm solving for. But D is the distance. Well, what is the distance that this satellite is traveling around the Earth? Is it the height of the shuttle above the Earth's surface? Is it the mass of the space shuttle? Is it the radius of the Earth? Unfortunately, it's not any of those. And we really need to think about what this question's asking. So if we look back at our diagram really quickly, we're going to see that here is our satellite or space shuttle, whatever you want to call it. Here is the Earth around, and then here is the orbit that it takes. Well, the distance that it's going around, and this should be more elliptical, kind of circular, but kind of looks like an egg right now. And the distance is actually the orbit that I just drew. And if we're thinking about this in terms of a circle, all we need to do is find the circumference. So D is actually going to be equal to the circumference. And what is the circumference? Well, in case you forgot, I actually give that to you on the top of the page. And that's 2 pi times r. Something important we need to remember, though, is that r is not the radius of the Earth. It's going to be from our satellite to the center of the Earth, because that is the orbit. It would have helped if I drew a better picture, but you get the idea here, that this is the center of our circle. If we go up and look at our other one, you would see it a lot better, but it's fine. So r, again, is going to be the height of the satellite above the Earth's surface plus the radius of the Earth. Once I have all of this information, I can just go ahead and plug it in accordingly. I'm going to go ahead and rearrange this equation a little bit. So instead of D, I have 2 pi r, which is equal to velocity times period. I'm solving for period, so I just divide by V, and I find out that my period should be equal to 2 pi r over V. Plug in all the numbers that we have above. Here's our V. Here is our r value. And then pi, we know, is just pi. Once we do all that, we figure out that our period should be equal to 5,495.54. What's the units, though? Well, if we've been paying attention, we noticed that we had velocity in here, and velocity has the units of seconds. Since we're ending in time, we're going to end with those units. So this is going to give us 5,495 seconds. It wants us to convert this into meaningful units like minutes, hours, and days, all that good stuff. So if I want to convert this into minutes, I'm going to have to divide by 60. So divide by 60, I find out that 5,495.54 seconds is really just 91.59 minutes. Convert this into hours now. Well, divide by 60 again. There's 60 minutes in an hour. That gives me 1.54 hours. And then lastly, convert this into days. All I need to do is just divide by 24 because there are 24 hours in a day. So if I do that really quickly, I'm going to find out that the satellite takes 0.064 days to orbit the Earth. All right. And later on in this class, we're going to do some problems with geosynchronous satellites. And the time that we get, you'll realize is a pretty interesting time relative to the Earth. Something I just wanted to mention, guys, before we finish these notes, is that if you take a look at this little GIF I have on screen, you're going to notice that I have an object orbiting around a circle. So that's going to have some uniform circular motion. And the velocity, like we mentioned before, is always pointing tangent to that orbit, but you'll see that the acceleration is pointed towards the middle. The reason being is that we know net force equals ma. Acceleration is going to point in the direction of the net force, and since the net force for uniform circular motion is a centripetal force, the acceleration and the force are going to point towards the center.